Okie dokie, everybody. The 2022 free response questions video key. So make sure you're familiar with these problems before you watch the key, because I kind of skip over even saying what the question is and just jump right into the problems. So familiarize yourself with them first, and then watch the key. So here we go on number 1A. Now remember, you have a calculator for this. It says write but do not evaluate an integral expression that gives the total number of vehicles that arrive in the toll plaza. So this is the rate at which cars arrive. So remember, if you do the integral of a rate, it tells you how much that thing changed. So since we know the rate at which cars arrive, the integral will tell us how many cars arrived. In this case, from t equals 1 to t equals 5, which is from 6 a.m. to 10 a.m. because 5 a.m. is t equals 0. But they also tell you right here t equals 1 and t equals 5. All right, B, find the average value of the rate in vehicles per hour at which vehicles arrive at the toll plaza from, again, t equals 1 and t equals 5. Average value of the rate. That means you want to find the average value of that function, a of t. Average value of a function is integral divided by interval length. And of course, you just math 9 it. And there you go. C says, is the rate at which vehicles arrive increasing or decreasing? So you want to know if the rate is increasing or decreasing. This function right here, is that function increasing or decreasing? Anytime you want to know if any function is increasing or decreasing, you look at that function's derivative. So I did a prime, and it wants to know at 6 a.m., which is t equals 1. So a prime of 1 is this answer, which remember you can just use math 8. This answer is greater than 0. That means that the function a is increasing at t equals 1, since a prime of 1 is greater than 0. Okay, and then part D, let's see, a line starts to form. Find the greatest number of vehicles in line. So the number of vehicles in line is the integral. Well, it's this function right here that they gave us. So that's the number of vehicles in line at any time, but we want to find the greatest number of that. So that means we want n prime. So here's n prime. The derivative of the integral is just the function, except notice how there's a t plugged in there now. That's the famous foot tattoo problem. And we want to know when this equals 0. And so you can just graph this and find when it equals 0, or set these two things equal to each other and find those intersection points. And that occurs at those two t values. And then down here, I used those values. A, I labeled as this number, and that was the moment that cars start getting in line, so there were no cars in line at that point. And then I did B, so I did, which was a thing defined for us. Maybe I didn't write it down. But B is this number. I thought that was given to us somewhere. But in any case, I'm calling this value B. I should write that down somewhere, like I wrote that down. So this value is B, so we're doing the integral from A to B of this, and you just math 9 that, and that gives you that. And then at 4, which is when it ends, and that is that. And so you know the greatest number of vehicles in line is this amount of vehicles at t is approximately that. You could also do like a sign chart analysis and explain how you know that the maximum occurs at this time and how this time is actually a minimum, and that this time is also a minimum at t equals 4. So you could explain that as well. All right, on number 2, we have a graph here that we want to find the area of the region enclosed. So that's the integral of top minus bottom from -2 to that number right there, which they're calling that intersection point B, but you have to find that intersection point. And so you just do the integral from -2 to B of top minus bottom to get you that. For part B, it says let h of x be the vertical distance between the graphs. Is h increasing or decreasing at this number? So similar to the last problem, function h is the vertical distance, which is just f minus g. And so we want h prime of -0.5, which is just f prime minus g prime. at negative 0.5. But you can just math 8 it. So you use your math 8 functionality, get this number, which is negative. Since the slope of h at that point is negative, h is decreasing at that value. Part C, very typical type of question here. The region enclosed by the graphs is the base of a solid. Cross sections of the solid taken perpendicular to the x-axis are squares. Find the volume of the solid. So that means we have like a cross section like this, and this square is coming up out of the screen right at your face. If you can, I think that looks pretty good if you can visualize that three-dimensionally. And so the cross section is a square. The length of the square runs from curve to curve. So the length of the square is f minus g. So the area of the square is the side length, f minus g, squared, and then times your thickness, dx, to get volume. And you just integrate that from negative 2 to b again, giving you that. Okay, and then part D, it says a vertical line in the plane travels from left to right. The vertical line is moving at a constant rate of 7 units per second. Find the rate of change of the area of the cross section above the vertical line with respect to time when the vertical line is at position x equals to negative 0.5. Sounds like a lot, but what's happening is there's a vertical line like this, and it is moving across like this, and it's moving at a rate that we know, because it was given to us, of 7 units per second. It wants the rate of change of the area of the cross section. Well, the cross section is still just right here. It says along the base of the solid described in part C. So the cross section is still a square. So the area is that. And so doing the derivative of this is what I've shown over here. So I did the power rule, kept the inside the same, multiplied by the derivative of the inside. So the derivative f of x, though, is derivative of the outside f prime, keep the inside the same, times the derivative of the inside. This is a related rates problem. X is changing as time changes. So this is times x prime or dx dt. So is that when you have g prime. And then you can plug in everything you know that's your dx dt value, and x is negative 0.5. So you got to find f of negative 0.5, g of negative 0.5, f prime of negative 0.5, g prime of negative 0.5, all of which you can just do on a calculator. Make sure you can actually get that answer. A lot of times people get the setup correctly and then don't evaluate it correctly. All right, number 3. All right, so we have graph of f prime. It wants us to find f of 0 and f of 5. So this is where they tell us a value of f. And so we can get f from f prime by doing integrals. But when you do the integral, you got to choose your bounds wisely. You want this to be a bound and this to be a bound. And that is because if you do the integral of f prime from 0 to 4, it is equal to f of, because the antiderivative of f prime is f, so antiderivative of upper bound plugged in minus antiderivative of lower bound plugged in. We can calculate this from areas from the graph. F of 4 was given, and f of 0 is what we want. And so that's why you choose these bounds. So the integral from 0 to 4, again, is going to be this area right here. So it's just the area of that half circle. Since it's below the x-axis, it's negative, so you get negative 2 pi. This is 3 because it was given, so solve this equation for f of 0, resulting in that. The second part of A, f of 5, is the same thing. Just go from 5 to 4. Just be careful when you go from 5 to 4 that the value of that integral, 5 to 4, is actually going to be negative even though it's above the x-axis because we're going this way, 5 to 4. So there you can see the work for that. Part B, find the x-coordinates of all points of inflection on the graph of f. So points of inflection on, which is where concavity changes, but on an f prime graph, those are maxes and mins. And so that's at x equals 2 and x equals 6. It's maxes and mins again because inflection points are where the second derivative changes from positive to negative. But if the second derivative changes from positive to negative, that means the first derivative changes from increasing to decreasing. Or it could change from negative to positive, which means, so if f double prime is negative, that means f prime is decreasing, because f double prime is the slope of f prime. So when f prime changes from decreasing to increasing, that means f double prime changed from negative to positive. And that is the definition of an inflection point. Okay, part C, let g be this function. On what intervals, if any, is g decreasing? So you want to find a decreasing function, or find when a function is decreasing, so find its derivative and find when it's negative. So here's g prime is equal to f prime minus 1. So we want to know when f prime of x minus 1 is negative, and that occurs from 0 to 5 because this is the graph of f prime, but the function we're looking at is f prime minus 1. So just shift everything down 1, and so this part of the graph is going to be like down here, and it's going to look, something like that, roughly. And so everything's just shifted down 1. So now you have this additional part of the graph that is below the x-axis, which is that is the graph of g prime. So that's where g prime is negative from 0 to 5. And that means that is where g is decreasing. Part D, find the absolute minimum value for the function g. Well, if you're finding a minimum, again, you want to look at the derivative, and you want to know where that equals 0 for a critical point. And that is when f prime of x equals 1, and f prime of x equals 1 at x equals 5. So x equals 5 is a critical point. And then I also looked at the endpoints, 0 and 7, and I evaluated g by doing this at all these values, and then compared. And then determine that the absolute min occurs at x equals 5 because this is less than that, and there's a maximum at 7 because this graph is above the, well, it's actually this graph shifted down 1 because we're talking about g, but it's still going to be above the x-axis, which means g prime, that would be g prime is above the x-axis, which means g is increasing until this point. So whatever the graph of g looks like, it could be down here, it doesn't matter, but it's going to increase until it gets there. So that's a maximum. Ignore that, that's not what the graph looks like. I was just drawing random things. So that's the rationale behind that problem. All right, we have an ice sculpture melting here. It says approximate r double prime of 8.5. So to approximate, that's the slope of r prime. So to approximate slope at a point, you can find the slope between 2 points. So since it's at 8.5, find the slope between 7 and 10. And so that is the work I've shown right here. Right there, it's y2 minus y1 over x2 minus x1, which is just 3. And you get 0.2 centimeters per day squared. Is there a time for which r prime equals -6? So on this one, we have r prime values right here. So does it ever equal exactly -6? Well, yes. You do have to say that that r prime is continuous. We know r prime is continuous because the radius is a twice differentiable function of r, which means if it's differentiable, it's continuous. So do say it's continuous, and then just show the two values where -6 lies between those two. So you can read that to see the explanation. Part C, use a right Riemann sum of 4 subintervals to approximate the value of this integral. So it's the integral of r prime. So we're going to go for a right Riemann sum. This interval has a length of 3, but you use the right endpoint, which is this work right here. This has a length of 4, but use the right endpoint, which is this. Length of 3, use the right endpoint, which is this. And you don't have to simplify algebraic expressions or numeric expressions, so that should actually be acceptable as your answer as long as you use appropriate units. And then part D, the height of the cone decreases at that rate. I'll let you guys read the problem. But we're trying to find the rate of change of the volume of the cone. So volume was given to you to be this. Now, as the height decreases, the radius also changes. So both things are changing as time changes. So this is a related rates problem. So, and you got to do product rule. So here's the derivative. And then dr dt at t equals 3, that's just r prime. which was given to be negative 5. And then dH dt is given to be negative 2. So I plugged all those numbers in. Again, you don't need a simplified version of this, but if you did simplify it all the way, it ends up being that. Okay, make sure you can do this derivative correctly. That's the key point here. Another related rates problem. You will see related rates on the AP exam for sure, just whether or not it's free response or multiple choice. And it's not on there a lot, but it is on there. And I think it's something that's very doable as long as you review that stuff. All right, so now we have a slope field, and we're supposed to draw the solution curve that goes through the point 1, 2. 1, 2 was already drawn for us. You can't see mine anymore. So just make sure you follow the slope field lines. Notice where the slope is 0, where the slope field lines are 0, I have a max or min. I might have missed a little bit over here, but I could probably draw that better because it should really come up here, flatten out like that. So I should have a max or a min right there. So I should move that over a little bit, I guess, but that's okay. Look at the scoring rubric for this one too, so you can see exactly how they score that. I'm going to actually make that a little better. Whoops. So, not sure what thickness I used. This should come up like this. Oh, it switched. This should come up right here. I need to have a maximum right there. That's a little bit better. All right, so in any case, there you go. And then we have, let's see, tangent line approximate, or write the equation for a tangent line, and then we're going to approximate. So a tangent line at this point, so we need the slope at the point 1, 2. So plug 1, 2 into this to get your slope. And I got 3 halves. I just showed it right there, what I did. So I evaluated the derivative at that point. So I got 3 halves, and then I did point slope. Y minus 2 equals 3 halves times x minus 1. And then at point 8, you're just going to plug point 8 in for x and then calculate that. Again, I don't think you need to calculate it, but you do need to say y equals. So like, you can just plug in point 8 right there and add 2 to both sides, and you can leave your answer like that. For part C, it's saying the second derivative is always positive. So then it asks us if our approximation is an overestimate or an underestimate. Since the second derivative is always positive, that means the function is concave up. For a tangent line approximation, look where the tangent line is, it's always below the curve. So, since the second derivative is positive, f is concave up on this interval, therefore the approximation is an underestimate because it's a tangent line approximation. Remember, it's not the same for an RRAM or LRAM. That is based on whether or not the function is increasing or decreasing. And then use separation of variables. So I already separated the variables here by, go to the original thing, you just divide by this, whoop, get that over there and multiply by dx. So that's where this came from. Common mistake here is to say that the antiderivative of this is natural log. That is not true because it's not. If it was just y plus 7 and no square root, it would be natural log of absolute value of y plus 7. But that is not the case here. This is y plus 7 to the negative 1/2. So I add 1 to the power, divide by the same number. So I'm dividing by 1/2 or multiplying by 2. And then this 1/2 just stays there. The antiderivative sign is negative cosine, which is where that negative comes from. Then, since if I did the derivative, I need to multiply by pi over 2. I'm dividing by 2 over pi. So 2 over pi times this 1/2 gets me that in the end. Or you can use U substitution if you're more comfortable with that. Put your plus C. This was our initial condition. Find C. Then put your C in. I already divided by 2 for this 2 right here. So I kind of skipped a step. And then square both sides and add or subtract 7. So hopefully you can follow that algebra there. All right, and then number 6, we have 2 particles. We have the position of one and the velocity of another. Find the velocity of P. The velocity of P is at time t, so not at a specific time. The velocity is the same as the derivative of the position, and so do the derivative of this and get that. Then we need acceleration of particle Q. And then, so acceleration of particle Q is just the derivative of particle Q. So that's where that comes from. Remember, this is t to the negative second, and then you just do power rule. Then it's asking us, is the speed, find all times when the speed of particle Q is decreasing. So you want to know when the speed is decreasing. But speed is decreasing when velocity and acceleration have opposite signs. But the speed of particle Q is always increasing, since the acceleration is always going to be negative, and the velocity, which is this, is always going to be positive. So that means the speed is always increasing, because the velocity and acceleration always have opposite signs. Part C, find the position of particle Q. So position is displacement plus initial position. Here's our initial position. So find the displacement, which is the integral. And it wants it at time t. So that is, do the integral, find your antiderivative, put a plus c, use your initial condition to find c, and then just put your c in right there. So this is the position of particle Q at any given time. So now we have position function for Q, and we have a position function for particle P, which was given, remember? And then it wants to know, as t goes to infinity, which particle will eventually be farther from the origin. So really you're just doing a limit. A limit of this as t goes to infinity is 6, because this is actually on the bottom. So this gets really big on the bottom, which means 0, so you get 6. That's just Bill Gatesing. And the position of Q, same thing. This goes to 0 also, because this is on the bottom, so you get 3. And so particle P will eventually be farther from the origin. That is it. If anything wasn't entirely clear, which I'm sure there are some things that weren't, make sure you ask me the next time you see me. Peace.